So we talk about the first. Uh, so the first section we will talk about the homogeneous linear uh, ODE of a second order. Okay. So we have the second order equation is the equation that in which we can find the second derivative of the unknown function. Specifically, we have y double price equal to px. This is the function of it, and this is the coefficient. Y price equal to q x and y equal to r. This is the right side. We have the r. So this is so because any function can be written in the form of this equation. We have the uh, linear linear second order equation. So if we can write this one Ts, Qs, and Rs, so we have the linear function and the linear form of the second order equation. In this case, similar to in the previous, we have the y in the section concretely in the section 1.5. We have already discussed the first order, the linear first order uh, differential equation y px y equals to r. Indeed, the linear because it can be written down in the form of by the coefficient px and rs. So and similar, so we have the linear second order linear ODE. Okay, so we have the second order linear ODE, 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 linear ODE. In this case, if we have the both Rx in the right side of the equation equal to 0, so we obtain the homogeneous linear ODE, homogeneous because it is 0, 0. So in the first chapter, in the first section of the chapter, we will discuss about the homogeneous linear ODE for the case of R is equal to 0. Otherwise, if the RS is not 0, so we have the non-homogeneous. ODE. And remember that the second order linear ODE is very important when we model many architecture, especially the AC circuit. For example, we have the y prime plus ps y prime plus 2x y equal to 0. Um, so um, for example, specifically we have first y prime plus 25 y not right. So equal to e exponential minus x and cosine and x. This is the non-homogeneous linear equation because in this case we can assume that e is equal to 0, Qx equal to 25, and this is Rx not 0, so this is non-homogeneous. Homogeneous. And for example, if we have, for example, we have x, y double price plus y price plus x time y, so equal to 0, this means we have homogeneous. And this is linear equation because we can say, because we can train to the standard form of by move x to this one, x divide both triangle equation for x, so we have x and 0 x by 0, and we have the standard form y double price equal to y price over y plus x over x by equal to 1y equal to 0 will be homogeneous linear second differential equation. As, okay, that is the concept of the homogeneous linear ordinary differential equation of second order. So the next step, so we try to find the method how to show the how to show this equation, how to show this equation plus tx y y price qx y equal to 0. So we have to show that this to find the root, to find the solution. Okay. Before to show before dive into showing this diagram, so we will discuss some characteristics of this equation. So in the first uh, chapter, we discussed about the first order of the first order ordinary differential equation represented by y prime equal to f as a function of s, or specifically in the linear form, we have prime plus tx y equal to rs or equal to maybe 0 or not 0. And the solution for this equation should be y equal to x, 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 x. Or we can write another form, namely implicit form, uh, use x, y function and equal to c. We already learned in the previous lesson. So this is the solution, and we have one solution, and we namely general solution or particular solution. That means we can find um, arbitrary value of c. Okay, and in second, a little bit different in second equation and the second order equation. Um, we have more than one solution. For example, um, y double prime could be x, y prime could be q, sorry, plus q x, y equal to 0. We will discuss about the homogeneous, not non-homogeneous. So we have the more than one solution y1 and y2. We have two solutions for this one, and two solution equal basis of solution. Basic of solution. And this we can remember. Remember, you can we can consider that is solution, and this is also solution of this equation, and I know I name it as the first equation, the equation one. So, and we have the first concept theorem, like that um, for homogeneous linear ODE. Okay, any linear combination. So I will explain what the combination layer of two solutions. Um, so we can imagine that two solutions like that, and we call a basic of solution with more than one solution for this equation, especially specifically two solutions on on an open interval I is again solution of one. That means, and what is the combination? So this theorem states like that. So assume that we have the equation represented by the first equation, the second order homogeneous linear ODE represented by the first equation. So we have the I1 and I2 is the solution, and specifically this is the basic solution. We remember that if this is not exist in the first equation, but in the second order, so we have the basic solution. That means y1 and y2, and they satisfy this equation. Both satisfy, 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 satisfy this equation. So we can call the solution. So if y1 and y2 are solution of the second order equation ODE, second order ODE, so we have the linear combination of two solution, or the linear combination of y1 and y2 is also a solution of equation one. So what is a combination of two variable? Assume that we have the variable x and y, for example. So the combination, the combination, uh, linear combination of x, y is z equal to ax plus by. And the linear combination, that means the sum of two variables with the corresponding weight. Then we can have weight or the constant. It's simply like that. We multiply this one with the constant and multiply this one with constant. So we have the linear combination of two variables. And the linear combination of y1 and y2 equal to, we obtain the y, for example, equal to c1 or a or any arbitrary value, y1 plus c2 y2. This is the linear combination of y1 and y2, and more specifically in this case, the theorem states like that. So if we have the y1 and y2 is the solution, so we always have the y equal to c1 multiply y1 plus c2 multiply y2 is also a solution of the second order ODE. Uh, Specifically, the second order homogeneous linear ODE. So, and the lastly, finally, we have the form of the solution like that. This is the solution. The solution, namely the general solution of the second order homogeneous linear ODE. So we have this one. So in order to find a solution for the second order ODE, so we have to determine the first solution, and we also determine the second order, sorry, the second solution y2, and then we multiply by the arbitrary c1, c2, so we obtain a solution. And similar to the previous lesson, we use the initial condition to find the arbitrary value of C1 and C2, and we obtain a particular solution. To obtain a particular solution. So to conclude, for the session, for the concept of the solution, we can have like that. We have the second order, um, have the second order homogeneous um, ODE like that equal to 0. And remember that in the first section we consider it is 0 because we already discussed about the homogeneous. And the solution will be have y1, y2 is the basic of solution. The basic solution can be thought as a solution of this equation because it satisfies this one, and I name this one with the first equation. And we have the general solution, is a combination of the basic solution. The general solution is a combination, the linear combination, represented by y equal to c1 y1 plus c2 y2. This is the general solution for the second order homogeneous linear. Keep in mind we can give this equation for the solution of the second order. And what is the initial? So the initial condition is presented by the y of 0 or something. For example, for in common case x0. Okay, y x0 equal to k0. And remember that we have from this one, because in the general solution, we have two variables should be determined, C1 and C2. So it with only one, we cannot determine the C1 and C2. And the second condition is equal to y prime of x0 equal to k1. And from this one, from both conditions, we can determine the C1 and C2. So it should be made clear in the specific of example later. So, and this is what we um, what we say about the solution of the second order. Um, so keep in mind this one and this one and this one. And next, we have the we will